So after going over those 6 warm-up problems, you can see the answers up here for all 6 of those. Just remember, when we're multiplying, coefficients get multiplied with coefficients and radicands get multiplied with radicands. After we multiply, we try to make sure that all of our terms are simplified. And then if we're left with multiple terms and they're simplified, we would just try to add or subtract things that are like terms, things with the exact same radicand. So last class, we dealt with addition, subtraction, and multiplication. Today we're going to look at the final operation here, division. So doing division with some radical expressions. So the big key here is you cannot have radicals in the denominator, right? So you're not allowed to have any radicals or irrational values in the denominator. So the goal is to get all of our radical signs out of the denominator. And it is okay to have them in the numerator, but you just don't want to be dividing by a radical. So looking at the instructions here, first one is just telling us that our square root can be divided out. So just like with multiplying, we can still divide or reduce our coefficients with coefficients, right? So the outside values with the outside values, just like when we multiplied it, right? We can go coefficient with coefficient, try to reduce or divide those. And then also same thing with our radicals. We can take our radicands and simplify them or reduce them with other radicands. Sometimes when we do this, we get a perfect square down below, which we then can simplify, and we no longer have to worry about the radical in the denominator. If not, we're going to look at 2 different cases. One, we have just monomials, mono meaning singular term in the denominator. Then also what will happen when we have multiple terms or an expression in the denominator. So starting with our monomials, all we want to be able to do is multiply the numerator and denominator by the square root that we see in the denominator. This gets us a perfect square and gets the radical out of the denominator, right? So looking at number 1, coefficients with coefficients, if we could try to simplify them, we would try to simplify them, right? But a 15 over 2 can't be reduced or simplified. Once we look at our radicands, we try the same thing, checking our 7 divided by 3 under the radical symbol. Those don't go in evenly and cannot be reduced. So at this point, we recognize that in order to get our square root of 3 out of the denominator, what we're going to have to do is multiply both top and bottom by the square root of 3, right? So we're focused on getting the radical out of the denominator, so we're multiplying by whatever radical we see in the denominator. So the big thing here is we need to make sure we do it on top and bottom, because really when we look at that, that is a unit fraction, right? Just like if we were to multiply something by 4 over 4, that would be the same thing as multiplying by 1, so it wouldn't change the value. Same idea here, multiplying by square root of 3 over square root of 3, same thing as multiplying by 1. We're not changing the value of the original fraction. So let's multiply fractions just to refresh your memory, right? Multiply straight across the top. So when we do that, we get 15. Multiplying our radicands together, we get the square root of 21. Underneath, we multiply underneath there. We get 2 times the square root of 9, right? Multiplying our radicands. So what will happen here is we get this perfect square in the denominator, right? If we look at 9, it gets broken up into these 3s. We can then simplify that down by taking that group of 3s, moving the 3 out front. So 2 times 3 out front would get me a 6. And now I have no more radicals in the denominator, right? So looking at it, we end up with 15 times the square root of 21 over 6. So I would try to simplify the numerator as well if I could, just to see if I could reduce, but 21, or the square root of 21, if we tried to factor tree it right, would just get us a 3 and a 7, both prime numbers, not enough to make a group, and simplify that radical expression. So the goal here, right, is to make sure that there are no radicals in the bottom of the fraction, right? We don't want any radical symbols underneath. So looking at number 2, same kind of idea. This time we have an expression up top, right? So sometimes it's helpful to throw some parentheses when we have multiple terms to recognize that those things are attached. We don't want to try to go simplify the square root of 7 from down below with the same square root of 7 from up above, because the one up above is attached to the one through subtraction, right? So making sure we recognize not to reduce or simplify in that case. So just like our first example, this time we want to multiply by the square root of 7 is what we're trying to get rid of. So we need to make sure we do it on top and bottom. So let's do up top first. So up top, since we had 2 terms being multiplied by the square root of 7, we got to multiply each by the square root of 7. So when we do that, we end up with 1 times the square root of 7, or just the square root of 7 on the Second term, taking that square root of 7 times negative 2 square root of 7, we get negative 2 times the square root of 49. So on bottom, multiplying straight across the bottom, we get 3 times the square root of 49. So once again, each of these 49s under the radical can get broken down to 7 times 7, gets us a group of 7s. Same thing up here, gets us a group of 7s that we can move out front. So really, on the bottom now, we have 3 times 7, which gets me a 21. Up top, really once we simplify that second term, and bring the 7s out front, multiply it times a negative 2, I get a negative 14. I'll put that one first, and then plus a square root of 7. So there, we've now what is called rationalized the denominator, meaning that we have got all the radicals out of our denominators. So let's look at up above. We talked about sometimes it's helpful to just kind of simplify it first, because then you could be left with a perfect square. So in example 3 here, as you look, we want to look at our coefficients, those numbers out front, right? So here we have a 4 and a 10. So even though 4 doesn't go into 10, both of them can be reduced, right? So as we reduce that down, really 2 goes into each. So if we divide both by 2, 4/10 is the same thing as 2/5. Doing the same thing here with our radicands, right? Looking at the 3 up top, the 12 down below, there's a value that goes into both of those. So if we divided or reduced each of those, up top we would have a 1, on the bottom a 4, right? So looking at it, we want to make sure we just reduce that. So 3 over 12, same thing as 1 over 4. And as we reduce, we never want to try to reduce coefficient with radicand, right? It's always coefficient with coefficient, radicand with radicand. So what this has done is left us with a couple perfect squares. So now we don't even need to multiply. All we need to do is simplify down these terms. So once I take the square root of 4, which is 2, multiply it times the 5, I get 10 in my denominator. Up top, the square root of 1 really is just 1, right? So really up top, we'd have a 2. And then now we can simplify that even further, right? So reducing that fraction down, we end up with our answer of 1 over 5, or 1/5. Look at this next one. Once again, we can take our radicands and reduce them if possible, which is always want to start there, just so you work with smaller numbers anyways. But a lot of times you can end up with a perfect square. So in this case, I know 6 doesn't go into 27, but there is a number that goes into both 6 and 27. So that would be a 3, right? So if I reduce this or divide each of these things by 3, the result would be a square root of 2 over square root of 9. So what's nice about that is now in the denominator, we've been left with this perfect square root in the radicand, right? So we simplify that down. Square root of 9 is the same thing as a 3. So we're left with the square root of 2 over 3. Now we don't have any radicals in our denominator. Let's try the next one. So the next one looks a little different than most, because here you can see that the radical is going over the entire expression. It's nothing more than just saying we have the square root of 3x over the square root of 50, right? So it's saying that really we're just dividing our radicands. So as we start to try to, you can either simplify it first, right, which probably work with smaller numbers, be helpful to do. So looking at the 50, I can try to simplify that first into 25 and 2. 25 breaks into 5 and 5. Gets me a group of 5s, right? So now I can simplify the bottom down to just 5 square root of 2, which is helpful because now we don't have to multiply by the square root of 50. We can just deal with the square root of 2. So up top, we still got 3x under the radical symbol. So problem is that's not our final answer because we still got a radical down below. As we look at the denominator, we have the square root of 2. So in order to get rid of that, remember we're going to multiply top and bottom by the radical we see in the denominator. So here we're multiplying top and bottom by the square root of 2. So when we do that, up top we get the square root of 6x. Underneath we get 5 times the square root of 4. So once again, by doing that, we got this perfect square in our radicand. So once we simplify can bring the group of 2's out front, multiply it by the 5 to get a 10. Up top, we still have the square root of 6x because that one is not going to get us any pairs of prime factors that we could simplify it. So notice here, once again, the denominator, when you're done, should not have any radicals in it. In this case, you see that there's no radicals left in the bottom of the fraction. So looking at number 6 now, same kind of idea. We want to make sure that we get the radicals out of there. Recognize that up top we have 2 terms, right? Join through subtraction, 4 minus the square root of 2. Sometimes helpful to throw parentheses around there to make sure that once we multiply, we do it to both the terms. Once again, you don't want to try to reduce a singular term or monomial in the bottom with just an individual part of an expression up top. So really we were going to start by trying to get rid of our radical down below and multiply everything by the square root of 2 on top and bottom. So let's do up top first. So we'll throw in the parentheses, helps to remind me I need to distribute that, square root of 2. So 4 times square root of 2. And once we multiply square root of 2 times negative square root of 2, we get negative square root of 4. So out of those, we can simplify the last term, which ends up just becoming a negative 2. So we put that first. So now we've simplified what's up top. Down below of our fraction, we would have 6 times the square root of 4 once we multiply straight across our denominators. Once again, we're left with this perfect square, which gets us a group of 2's. Move out front, multiply times that 6 out there. And what will happen is we end up with a 12. So what we can do here, and what you want to try to do here is recognize that looking at your coefficients this time, we have 3 coefficients, right? We have the negative 2 up top, the positive 4, and the positive 12. If they can all be reduced or divided evenly by the same number, we would want to try to go ahead and reduce all of those. So in this case, 2 goes into each one. So as I divide each by 2, I'm left with my final answer, negative 1 plus 2. Never mess with the radicand, right, as we're simplifying coefficients. And then 12 divided by 2 would get me a 6. So as you flip the page, take some time real quick. Try example 7 and 8 in your group. So go ahead and try example 7 and 8 in your group. I'm trying to get that denominator rationalized by getting the radical out of there. Let's go ahead and pause the video. All right, so looking at number 7 and number 8, obviously number 7, once again, we had an expression up top, helpful to throw some parentheses around it to make sure that once we multiply top and bottom by the square root of 10, and we multiply both terms up top by the square root of 10, so that got me 3 square root of 20 minus the square root of 50. Then I wanted to simplify each of those. So both of those terms simplified down to 6 square root of 5 minus 5 square root of 2. Underneath on the denominator, when we multiply by the square root of 10, we got the square root of 100, which is the perfect square, simplified all the way down just to the value of 10. So when we looked at those coefficients this time, though, the 6, the negative 5, and the 10, those cannot be reduced, right, because there's not a number that would go evenly into all 3 of those. On number 8, there, once again, expression up top, we're multiplying. There's only a monomial, singular term down below. So we're multiplying by the square root of 3 on top and bottom to try to get rid of the radical on the bottom. So on the bottom, 5 square root of 3 times square root of 3 gets me 5 square root of 9, which simplifies down all the way to just a 15. Up top, when we multiply, we get 3 square root of 3 plus the square root of 18. Once we simplify those terms, first one didn't simplify, but the second one simplified down. So then our numerator was a 3 square root of 3 plus 3 square root of 2 all over 15. This time when we look at the coefficients, we got a 3, and a 15. All of those are divisible by 3. So we want to reduce that down, our coefficients, by dividing each by 3. So then we end up with just 1 square root of 3 plus 1 square root of 2 over 5. So notice we didn't do anything to the radicands as we tried to reduce our coefficients. So that is the first type of problem that you could see, is having a monomial or a singular term with a radical in the denominator. All we need to do is multiply both top and bottom by that radical in order to get a perfect square. As long as we're dealing with the square root symbol, That'll eliminate the radical down below. And then we just want to make sure we are also multiplying the top by that same square root. So that way we don't change the value of the fraction. Second type problem we're going to look at today is when we have a binomial on the denominator, right? So that's a vocabulary term we talked about earlier this year. Binomial meaning two terms. So denominator, bottom of the fraction. We have two terms in the bottom of the fraction on these problems. What we're going to do is multiply the numerator and denominator by the conjugate, right? So what a conjugate is, it would be the exact same terms with the opposite operation in between. So you can see there the conjugate of a plus b would be a minus b. Same with vice versa, right? The conjugate of a minus b would be a plus b. So same terms in the parentheses, right? Just the opposite operation in between. So the whole reason that we're going to do that is so that we get our radical out of there, and you'll see how that works. So on number 9, first off, we don't want to try to reduce because really our coefficients are not all the same. Really, there's this coefficient of a 1 there, so we don't want to try to reduce right away. So the conjugate this time of our denominator would just be a 3 minus the square root of 3. We need to make sure we do the multiplication up top and bottom. That way it's like we're multiplying by 1. So let's do up top real quick. This time I'm going to take 12 times each of those. So it gets me 36 and minus 12 times the square root of 3. Underneath, let's talk about multiplying these conjugates together. So if I throw some parentheses around it, now you can see we're taking 2 terms times 2 terms. So we really have 4 different multiplication operations we should be doing. So really 3 times 3 gets me a 9. 3 times negative square root of 3 gets me negative 3 square root of 3. Square root of 3 times 3 is a positive 3 square root of 3. And the positive 3 times the negative 3 would be negative square root of 9. So the whole goal here is to get rid of the radicals. And what you'll notice is if you do the FOIL acronym, those 2 middle multiplication operations, so the outside terms and the inside terms, those will always cancel out as long as you picked your conjugate correctly. So if we look at those 2 middle terms, negative 3 square root of 3 plus 3 square root of 3, remember like terms because they have the same radicand. Then you're doing the operation with the coefficients. Negative 3 plus 3 is just a 0. So 0 times the square root of 3 would be just a 0. So really those should always start to cancel out for you. So really you just need to simplify this last one here. Square root of 9 is a group of 3's. We're going to move out front, becomes a negative 3. Since the negative 1 out front, so really underneath we have a 9 minus 3, which would be the same thing as a 6. So that 6 is in the denominator. Now this time as we look at these coefficients, all of them are indeed divisible by the same value. In this case, 6 would go into each of them. So really we want to divide everything by 6 to get our final answer. Just the coefficients, right? We're not touching the radicand. So 36 divided by 6 gets me a 6. Negative 12 divided by 6 would be a negative 2. Then we put on the radical 3. Underneath 6 divided by 6 would be a 1. So if we have 1 in the denominator, you don't necessarily need to include it, but just to show you how we reduced each of those coefficients. Let's look at number 10. Number 10, we got, once again, this time a binomial up top, binomial down below. So as we start to try to multiply with the conjugate here, the conjugate, remember you're focused on the denominator. This time would be 2 plus the square root of 7. So same exact terms, opposite operation in between. The whole point of that is to get rid of our radicals. So let's do the 4 operations up top first. So we got 4 times 2 is an 8. 4 times square root of 7 be 4 square root of 7. 2 square root of 7 times 2 would be another 4 square root of 7. And lastly, that 2 square root of 7 times the square root of 7 gets me 2 square root of 49. So before we go further, right, looking at it, the last term after we multiply can be simplified, right? Gets me a group of 7s. I bring out front. So that term, 7 times 2 becomes a 14, right? So once we simplify that term, it simplifies all the way down to a 14. Now we can try to combine it with any like terms, right? So we have the 14 and the 8, those combine, give us a 22. Our 2 square root of 7 terms can combine. 4 square root of 7 plus 4 square root of 7 gets me a total of 8 square root of 7. So simplify the numerator after we multiply. Now we can move on to the denominator, or underneath the fraction. So down below, 2 times 2 is a 4. Once again, you start to see you can skip these middle two, but 2 times square root of 7 would be a positive 2 square root of 7. Negative 7 times 2, negative 2 square root of 7. Last one, negative 7 times square root of 7 is just a negative square root of 49. So as we start to simplify, last term gets simplified, becomes a negative 7. Middle two terms will always cancel out when we multiply conjugates. So underneath there, 4 minus 7 takes me to a negative 3. So as I check, right, as long as my coefficients cannot be reduced, meaning my 22, my 8, and my negative 3, there's no number that goes into all of those. So we need to go ahead and leave that as our final answer. If there was a value that goes into all three, we obviously want to divide all three by that value as we reduce that expression. All right, so give this last one a try with your group as well. So multiplying by the conjugate on top and bottom. So you can pause the video if you need to. Here's that last example for you. Once again, multiply by your conjugate, same terms, opposite operation. So multiplying top and bottom by the square root of 5 minus 2 square root of 3. This time after we finish multiplying and simplifying our numerator, we got 2 square root of 5 minus 4 square root of 3 minus 5. We simplified that third term plus 2 square root of 15 all over after we multiplied or FOILed on the bottom. Got rid of all of our radicals, simplified down to 5 minus 12 or negative 7. Let's go ahead and spend the rest of the class time trying to complete that third assignment.